Now we have Bobby Pendry, a fourth-year neuroscience student in Dr. Brad Pfeiffer's lab. Bobby enjoys spending time with his various cats and houseplants, and his talk is titled Monitoring Brain Development in Real Time.
So, if I asked you to recall your earliest memory, what would come to mind? Maybe riding in the car with your parents, sitting in a car seat at like the age of 3, or seeing the family dog through the bars of your crib at the age of 2. It's probably something vague, only a fuzzy memory. Whereas if I asked you to recall a really memorable childhood experience, you'd probably be able to conjure every last detail about that time you fell out of a tree and broke your arm at the age of 10. Certain memories crystallize better than others, especially novel, emotional, painful ones. But on the whole, as we grow older, we get better at learning and remembering things. Now, when this process goes awry, it can result in intellectual disabilities that take hold in childhood and usually linger on into adulthood. Studying how exactly that happens is really challenging. A lot of scientific research is off limits for humans, especially human children. So my research in this area involves using mouse children, which might sound really odd because mice are so unlike humans in so many ways. They're small and furry, and they don't live as long as we do. But their brains develop a lot like ours do. And they behave like us in fundamental ways. And above all, they are resilient like we are. And that last part is important because studying deep brain activity in mice involves this rather invasive process of sticking wires into the brain, surgically attaching a device that holds the wires in place, and then plugging that device into a computer. If done properly in adult mice, those wires can monitor electrical activity in those deep brain areas while the mouse is able to run around and freely behave. Now, doing this in tiny little infant mouse pups has a lot more challenges. Most notably, they're simply too small to bear the size and weight of the device and still do normal things like eat, drink, and play. And so it's long been thought that this is impossible or impractical to do these experiments in tiny little juvenile mouse pups. Until now, I've refined the size, weight, and surgical process of implanting these devices in infant mouse pups, something that's never been done before in neuroscience. And so we can, for the first time ever, monitor this activity. This breakthrough allows us insight, unprecedented insight, into how the brain develops in real time in mouse pups as young as 19 days of age, which is the equivalent of a 2-year-old human child. And so now, for the first time ever, we can monitor the development of the brain in real time from infancy all the way to adulthood. And doing this in normal mouse pups, wild-type mouse pups, comparing them to ones that are genetically predisposed to an intellectual disability, we observe subtle differences in how their brains crystallize brand new memories. And these subtle differences can go a long way towards explaining things like how children with autism remember certain things extraordinarily well, but aren't so good at learning and remembering other things. And my research brings us a lot closer to understanding how and why that is. Thank you.